Hello. So, in this video we are going to be covering or perhaps reviewing the various types of numbers. So, first up on our tour of numbers are the natural numbers. So, natural numbers are whole numbers. So, particularly they have no sort of necessary fractions or decimal points, but these things are strictly positive. I'm going to put an asterisk there because it turns out, depending on who you ask, some people like to include 0, some people don't include 0. So the most popular one is the 1, 2, 3, 4, 5, 6, etc., not including 0. But again, if there's sort of any question, it's always a good idea to ask whoever's teaching your class or whatever situation you're in, whether or not they're counting 0. And as a forewarning, they will probably say something to the effect of course we count 0, that's what natural numbers are. Or, of course we don't count zeros, that's what natural numbers are. So just know that there's strong beliefs about that particular part. I also want to point out here a sort of subtle but important difference about this thing, which is that we say no necessary fractions or decimal point, meaning that if we write something like 4 over 1, that is a fraction, like it has a fraction form, but that would still be considered a natural number because it's still the number 4, it just is in a different format, right? So this sort of little thing to notice here is like if you can reduce it or sort of rewrite it into a way that is a natural number or whatever type of number, then that's what it is, as opposed to sort of messing with the format to make it look like something else. All right, moving on. So next up, we have integers. So integers are basically the same idea as the natural numbers, but now we're actually allowing the negative and 0 as well. So we're going to have, the 1, 2, 3, 4, but we also have the negative 1, 2, 3, 4, as well as 0, but still whole numbers. Next up, rational numbers. So rational numbers are sort of these fraction things, but specifically they're fractions where the numerator and the denominator, these are both integers, right? So they aren't just fractions, it's fractions where we actually have sort of the ratio, which is why we say rational, but it's the ratio of these nice whole numbers, positive or negative. Now in practice, these actually can have a variety of forms because of how we happen to write numbers. So rational numbers, we define them as these sort of p over q things, where p and q are both integers, but they also sort of, the other format they have, which is just as legitimate, are these sort of decimal forms where they have either finitely many decimal points, so it sort of goes for a little while and then stops, or it can have infinitely many digits as long as it sort of has a repeated pattern. So as an example, we could have something like this, 3.1415926 thing, and since I stop at 6, then that means I have finitely many, right? I only have however many that is, so like 7 or whatever decimal points, and that's a rational number. And it's a rational number because if I sort of write a appropriate power of 10, it'll move that decimal point over, and so I can write it as this sort of ratio of integers. So it's not just like we're defining it to be rational, it is legitimately rational, I can write it as that fraction. Notice I don't have to necessarily write this in lowest form to show, right? As long as it's writable in some fraction, I'm good. I don't have to make it sort of the right fraction, as long as it's equal. The slightly trickier version is that that sort of infinite number of decimal points, but with a repeating pattern. So for example, we could have something like this, 2.34, and then 1, 2 repeating, right? That's what the bar over it means. Now, there's actually a trick to show how you actually get this thing to be a rational number. And I'm going to go through it just because you should always have seen this at least once somewhere. But this is not a thing that we're going to be asking you to sort of do in practice because it's sort of a trick you can look up and you rarely actually need it. So the process to make this a rational number, we're going to take that thing and call it something. We'll call it x, but I could call it balloon if I really wanted to. It's whatever. I just need a thing to keep track. Then I'm going to multiply this thing by a power of 10, where that power is how many repeating decimals there are. So since it's 1, 2 repeating, two numbers, I'm going to multiply both sides here by 10 to the second power, which is 100, right? So on one side, my x times 100 is just 100x. On the other side, I'm moving that decimal place over 2 points, which happens to coincide to this 234.12 repeating. Now, I can sort of write that 1, 2 as many times as I want. That's what it means to be repeating. I'm going to write it one more time for a reason of clarity. I don't have to, but that's why I have this 0.12, 1, 2 repeating, is that I'm going to do something in a second here. And the thing I'm going to do is subtract off that original x. So here I'm just subtracting x, but over here I'm going to subtract what x is, specifically that 2.34, 1, 2 repeating. And the idea is that that 1, 2 repeating part in both places overlap perfectly, so they cancel each other out, and I'm good. So what's left over is just that 234.12 minus the 2.34. So I have that 232.78, and that is equal to the 100x minus x, which is that 99x. All right, so now I can isolate x, divide both sides by 99, and then this looks really awful. I don't like having decimals and fractions together, so I can multiply the top and bottom by 100. And finally, I am at this thing where I have this sort of nice integer on the top, integer on the bottom. That means I have a ratio of integers, so it's a rational number. And if you actually sort of did that division out, you get back to that 2.34, 1, 2 repeating. All right, so that's a little trick to show / prove, not really prove because it was an example, but prove, using that sort of loosely, that these sort of repeating decimal digit decimals are also rational numbers. All right, next up, real numbers. Now this is going to be the most hand-wavy of definitions you're going to get. So real numbers are any number that you sort of deal with normally. I'm saying that because it turns out the actual mathematical definition of the set of real numbers is surprisingly deep and complicated and takes a couple plus years of sort of math major courses to understand. So we don't want to go that way. There's some deep magic happening in the background, but really all you need to know is that real numbers are sort of all of those numbers we've been thinking about. So it includes all the stuff we've already discussed, as well as things like square roots and pi and, you know, those things that aren't rational numbers that don't have those sort of nice repeating decimals. So by way of example, right, we can have negative whole numbers, you know, our integers type things. So -3, -2, -1, 0's in there, square root of 2 is in there, square root of 3 would be in there, that 3141596 over 10 to the 7th, that thing's in there, right? Like all the sort of typical numbers are in there. Now there is one that's sort of a little bit bigger, which you may or may not have heard of, and we will sort of talk about in this class, and that is the complex numbers. We're going to get there in a second. I do sort of want to, before we get there, mention, because I did technically mention this, the irrational numbers, those other numbers. So irrational numbers, those are the real numbers that we haven't talked about, the real numbers that are not rational. So those are the things that have the infinite many decimal digits, but no repeating pattern. So square roots, or really any roots that don't sort of simplify nicely. So that's an example. Pi, another example, right? It goes on forever and doesn't really repeat. E, another example. So there's sort of these other numbers that aren't, right? We've been looking at sort of building up the whole way, right? We had natural numbers, then integers were like a bigger thing, and then rationals were a bigger thing, and then reals were a bigger thing. But there's sort of this irrational numbers that's sort of off to the side, and we'll have a nice little diagram for that. But going back to our real numbers, we can go yet bigger, right? So these are the complex numbers that I mentioned. And these are sort of numbers that include some multiple of that imaginary constant I, where we sort of define I in this weird way because we want something squared that is negative, really in particular -1. So I squared being -1, that's how we sort of create these complex numbers. All right, so there's a lot of different types of numbers, and they're sort of related in a very sort of straightforward way, but it's hard to tell just from their definition. So by way of sort of demonstration, there's nice, I hesitate to say Venn diagram because there's a lot of concentric pieces in this. So we start with sort of the biggest group that we talked about, the complex numbers. Complex numbers are sort of all these different numbers, a subset of those, sort of a smaller piece of things that are all complex but sort of have their own thing. That's the real numbers, right? So all real numbers are also complex numbers, but not all complex numbers are real numbers. Then the real numbers split into two pieces that are sort of not, there's no overlap between them. That's what I was trying to mention earlier, where we have these sort of rational versus irrational, right? So we were sort of building up, and I wanted to make a sort of very clear note that we have this sort of irrational number set that's sort of separated off to the side somehow. So that's how we split up our real numbers. Then in our rational numbers, inside the real numbers, we have integers. So again, all integers are rational, but not all rational numbers are integers. Then within integers, we have the natural numbers. So again, natural numbers are integers, not all integers are natural numbers. Okay, so this is our sort of nice little infographic piece that has sort of how these things are all interrelated. Okay, so what did we do? Well, we talked about the types of numbers. So we started out with the sort of smallest in some sense set here, which is the natural numbers. Then we went up, right, a grouping to go to our integers, which are sort of the natural numbers, all those positive whole numbers, but now the integers include the negatives and 0. Then rationals, so we can talk about fractions of integers. Then we had that split, right? So we had the rationals, but then we had the irrationals, which are sort of unrelated, although they are related, right? Because they're sort of the not rational real numbers. But then we had the real numbers, which is sort of all the rationals and all the irrationals. And then finally, the biggest one, we had our complex numbers, which if you haven't heard of, if I doesn't ring a bell, don't worry about it. We're going to sort of dive into that one later on. Okay. So that is that.